What we're going to look at now would be our line of best fit when we're looking at data, especially data points that don't necessarily relate to each other, but we can see a relation from. If I look at this would be 1, 2, 3, 4, 5, 6 different data points that I have. I've got a data point for somebody who studied 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, and 6 hours. We can see here there is my line of best fits in there, and I can see that I do have a trend that shows us as the hours study increase, the score on a test also increases. Those kind of trend lines are the things that we can now look at and interpret. What I can do though from this line of best fit is I can find what that equation is and then relate that equation to what is actually happening in the graph. So what I can do is find a couple points on this graph that'll be really pretty points or good points to look at. And I think one point that I'm going to use would be here, because it looks like it's right on that graph. This point would be 3 in the x and 85 in the y. The other pretty point we'll use will be 5 in the x and looks like 92.5 in the y. So now if we want to find the equation for this line, since we do have a linear line, it's going to be a linear equation, which is y equals mx plus b. M being my slope, which is rise over run. B is my y-intercept. So first thing I do is got to find my slope, which is my rise over my run. To find my rise, I got to find my change in y. So I've got to find what the change is between 85 and 92.5. To do that, I could do 92.5 minus 85, and that'll give me a value of 7.5. My run is then going to be the change in my x's. I went from 3 to 5, that gives me 2. So if I am looking at my slope now, which is my rise and my run, it's going to be 7.5 divided by 2, which is going to give me a value of 3.75. So in my equation up here, I've got y equals 3.75x plus whatever my y-intercept is. To find my y-intercept, I can, in this case, I can simply look at the graph. Looks like it's about, we'll go with 78. Now if I get rid of my work here a little bit, I've got my linear equation, which I found with my rise over my run of that trend line. Oops. I want my y equals back. So my y equals 3.75x plus 78. If we interpret this a little bit, that means that if I did not study at all, 0 times studied, I could expect a score of 78 because that is my y-intercept. And then for every hour that I study on top of that, I can add 3.75 to that. So if I study for 1 hour, it would be 78 plus 3.75, which is 81.75. If I studied for 2 hours, I would do 2 times 3.75 plus 78, and so forth, and so it would continue in that kind of pattern. Now if I wanted to see, say if I studied for 10 hours, how can I solve what my test score would be? Well, I just got to plug in 10 for x. So I'm going to say that my test score is going to be 3.75 times 10 plus 78. So that gives me 37.5 plus 78. I can see that my test score is going to be somewhere around 115.5%, which is probably a little unrealistic. But that makes sense because this is just a projection. It doesn't account for the fact that really max test score is going to be 100%. Now, what we can also look at in this group of data, and I have a small set of data, so it's going to be easy to see, would be my correlation coefficient. My correlation coefficient is how closely related these numbers are to this line. We can either have a strong correlation, a weak correlation, a perfect correlation, or no correlation. In this case, we have a strong correlation since all of those dots are relatively close to that line of best fit. And from the beginning, we said as it increases, our value increases. That means we have a positive relation. And like we said, we have a strong relation. If I just look at correlation coefficients of my first one here, if I look at it, for the most part, I can see I have a negative trend. And I would say, since these are pretty spread out, it's a negative weak correlation, which would give me a value probably negative 0.5 in my correlation. If I look at the second one now, kind of the same thing now, except it's increasing. So I would say this one has a positive weak correlation, which means I can see that the numbers are increasing, but they're really not that close to that line of best fit. So that would be somewhere probably around 0.5 as well. If I scroll up a little bit, we can see here, now we're talking a much stronger correlation here, and positive. So it's positive, and it's strong since all of those numbers are pretty much right around those two lines. I would say that's going to be somewhere around 0.8 for our correlation. This example would be an example of a negative perfect correlation, since those will create a perfect line. A perfect negative would be negative 1.0. Perfect positive would be positive 1.0. If I look at this one here, really can't draw trend line anywhere that looks like it would represent this data. So what we call this one is no correlation, because there really is no line that looks like it keeps track of what these are going to look like. And of course my last one goes downhill, so it's negative, and I would say those are pretty close. We've got a negative strong correlation. We'll say it's about negative 0.8. So you can see the correlation just tells you how close those data points are to that line of best fit.